It's good to be back. If you had told me it would be 3.5 years in a pandemic before the second graph day, I wouldn't have believed you, but here we are. And actually, at that last graph day, I gave a talk similar to this, where I posed a question to the audience: what is the graph? You know, at the time, we were just launching Edge and Node's hosted service. We had just announced the earliest iterations of our protocol design. And by looking at the answer to this question through these three properties, you really could have predicted the next few years of what the graph's R&D and research would look like. Now, today, I want to revisit this question through two new lenses. One is looking at the graph as a blockchain protocol, and the other is looking at it as a decentralized infrastructure market. And my goal is to contextualize the work that's been happening in the ecosystem for the last few years, as well as the evolution of the graph that you can expect to come. Now, you might be asking, the graph is a blockchain protocol? You don't really hear it mentioned in that light too often, right? You hear queries, you hear indexing. This is kind of a strange framing. And I want to get you there, but to do that, first we need to do a quick recap of how blockchains have been evolving over the last few years. So here's the mandatory Bitcoin slide. In the beginning, there was Bitcoin. It was good, but the problem was it only really did one thing, right? It was the money app. And it was all kind of rolled into the other innovations of blockchain around consensus and having this distributed, data availability and state machine. A few years later, projects like Ethereum came along and said, hey, what if we decouple, the general compute layer and allow people to build their own, purpose-built application-specific smart contracts? But it was all still bundled in the same package, right? So consensus, data availability, smart contract execution, it was all happening within the same chain. Now, in the last few years, with the advent of technologies such as Rollups, as well as purpose-built chains such as Celestia or Arweave, we're seeing this great unbundling happen where these layers are starting to separate, and you're starting to see purpose-built layers in the stack that can each be optimized for their own purpose and scaled out independently. And this permits a whole new universe of design patterns represented by the columns that you see behind me, where the rows are the different layers in the modular blockchain stack that have been unbundled. And you can see that we can still do the classic monolithic architectures, we can do rollups, we can do validiums, and so on. And what I would like to pose to you is that there's actually a missing layer in the modular blockchain stack that's been underappreciated and underconsidered in the blockchain space up until this point. And to understand why I believe that's the case, I want to walk you through a few missing pieces that exist in blockchains today. The first is on the incentive layer. So we tend to think a lot about the incentives that exist in blockchains, such as the gas price auction, the block rewards. But there's also things that blockchains need to do to succeed that aren't directly incentivized, such as storing historical state, running archive nodes, doing data retrieval, right? A big part of the Ethereum and blockchain vision was being able to do light clients and warp sync, have decentralized block explorers. All of that stuff is not incentivized directly in the blockchain protocols that we have today. Furthermore, it's not possible to verifiably get all types of data off of the blockchains that we have today. If you're interested in account balances or transaction lists, great. But if you're interested in derived data or more complex filtered queries like ETH-GET logs, there's actually not a verifiable way to outsource these types of queries to a full node. Now, one way that you could approach solving this problem is to spin up a bunch of centralized blockchain APIs on top of the full nodes in this blockchain data supply chain. And indeed, that's what's happened. We see things like Infura, Alchemy, the OpenSea NFT API be very successful. But we believe, in a similar spirit to the MEV researchers that are looking at the transaction supply chain and observing that centralization at one layer in that chain can infect the other layers, we believe that it's necessary for the end-to-end blockchain data supply chain to be decentralized. Otherwise, the only ones with the incentive to run these full nodes, these archive nodes, are going to be centralized companies and will all be disintermediated from the benefits we hope to get from Web3 and decentralization in the first place. Indeed, Afri, a notable Ethereum core developer, famously said that if we all end up accessing Ethereum through Infura, the for Ethereum has failed. So I'd like to introduce a new concept to you guys today. Since this is Graph Day, you can probably see where I'm going with this. We're going to talk about subgraphs. But in this context, I want to talk about them as read-oriented rollups. And to understand why I'm using that label in this context, let's do a quick recap of what rollups do today. They're a classic example of this unbundling, where data availability and consensus stays on layer 1, but state machine execution moves to layer 2. And specifically, it's the transactions that are stored as like call data on Ethereum. And then you can either submit fraud proofs that a block on the layer 2 is incorrect, as in the optimistic use case, or in the ZK rollup use case, you can get validity proofs that every block is correct and can be verified on layer 1 in real time. Now, read-oriented rollups support either of these patterns, the optimistic or the ZK pattern. The main difference is that whereas traditional write-oriented rollups use a transaction-oriented state machine, where the users are submitting transactions with the expectation that they'll be sequenced in a certain way on the L2, be executed in a smart contract, read-oriented rollups are all about producing the derived data that's necessary to use blockchain data for specific applications. So they can actually do arbitrary event sourcing or map-reduce logic over any sets of triggers that exist on the layer 1. But nonetheless, they still rely on layer 1 for consensus and data availability. And so the new layer of the modular blockchain stack that I want to propose is this transformation layer. And that's really where read-oriented rollups shine. It's not so much about the user a priori having an expectation of how they're going to change state in these read-oriented rollups. It's more that the users can have taken arbitrary actions in the past, and these read-oriented rollups can be designed around the data that already exists on the chain. Importantly, they can support almost all of the design patterns that we see today. So I've talked more about rollups here, but the Validium pattern, where data availability is handled on a separate layer, is likely where subgraphs will need to go to support NFT use cases in the decentralized network, where all the metadata is stored on IPFS and doesn't have layer 1 data availability guarantees. Importantly, like all rollups, these are composable and scalable. So in the same way that you can have Validium rollups verified in an optimistic rollup or in a ZK rollup, you can also have read-oriented rollups built on top of layer 1s, other layer 2s, or indeed other read-oriented rollups. The case with subgraph composition and some of the data pipelined execution models that you'll hear about later today. And this composability through sharding is what gets us the scalability benefits of rollups, right? It's that each person can focus on the small shard of computation that they're interested in and the path, back to the layer 1 base layer. And when we think about scalability, it's not just scalability in a vacuum that we care about. It's really about unlocking more use cases for Web3. So it's not surprising that the first use cases that had product market fit were the store value use cases, because you can send one transaction and store value indefinitely. And as we move along the value per transaction curve, to the far side, we get to like an individual tweet where maybe the value per transaction is actually quite low. Everyone else's tweets, of course. Your tweets are great. The other benefit to read-oriented rollups is that they're natively provisioned and upgradable, at least as they exist in the graph. Because it's not important for the user to have an a priori mental model of how the state execution is going to happen, and it's really ex post definitions of the derived data, you can upgrade subgraphs, you can natively provision them all in the context of the graph using the curation mechanism that Yaniv walked us through earlier. But we'd be remiss if we didn't talk about verifiability, right? If we're making the argument that subgraphs, read-oriented rollups are part of the modular blockchain stack, then one of the most important things that blockchains do is they have these properties around verifiability. In the context of the graph, we like to talk about verifiable indexing, verifiable querying. For verifiable indexing, we support many of the patterns that we've seen today, with the caveat that it's a little bit more complicated, and we'll get to that in a second. And then on the other side, we want to make sure that once you've indexed a subgraph, that you can actually reach in, query the data that you're interested in, and have guarantees that that data is correct. Starting with verifiable indexing, let's look at one example of how we could approach this, which is using a ref-read game. This is a form of interactive fraud proof that's been put into production recently by layer 2s such as Arbitrum. In this model, you look at the execution paths of two different validators, and you can run a sort of binary search to figure out where they diverged in execution, and then recompute that single step of the computation on chain. So that's kind of where the scalability benefits come in, is that you really only need to process this tiny bit of computation on the layer 1 rather than the full computation. In the subgraph use case already, our WASM computation, which is the subgraph mapping, is already a little bit more complex than what you'd see in a typical WASM program. Yes, there are steps that are sort of native or endogenous to the WASM module, but there's also computational steps that are calling out for more data from another blockchain or calling out for data that had previously been computed in the store. And this is only going to get more complex as the subgraph execution model evolves to support higher performance use cases, as you're going to hear about from Sebastian of the Graph Council later today. And so what this means is that when we run this binary search to figure out where two subgraphs execution paths diverged, it might be that we're just rerunning an opcode on chain, but it could also be that we're witnessing in proofs from other systems, such as a EVM-based ref-read game, or a query proof, or a Merkle proof from an underlying blockchain. But the theory is there. This is really, at this point, an engineering challenge that our ecosystem needs to tackle together. On the verifiable query side, this is actually something that we've been thinking about for a number of years. This is a screenshot from a talk that I gave near DevCon. We weren't quite invited to speak at DevCon back then in 2018, where we presented this idea that maybe we could look at the database indexes that are in use today, the data structures that are used to power those indexes, and can we just come up with Merkleized versions of those indices? It seemed like a reasonable idea, and indeed that actually was part of what led us to stumble upon this new line of research that's called outsourced databases. This is basically a line of research in academia that describes a setting in which consumers can safely outsource queries to a server and trust the results without having any of that data locally on their machine. And this paper, IntegraDB, actually approached this problem using authenticated data structures on Merkle trees and traditional database data structures. But it wasn't quite as expressive and efficient as we might like. And that's kind of what led us to look at a different type of authenticated data structure called polynomial commitments. And as it turns out, with clever math, you can actually store all the data or represent all the data in a database inside of a polynomial. And these things have the nice property that they tend to be more efficient across a number of different dimensions, but they also compose nicely with arithmetic circuits, which are one of the magical building blocks that powers zero-knowledge proofs. And indeed, there's another notable paper in this line of research called vSQL that followed exactly this approach. And the exciting results, exciting experimental results that you'll be hearing about from Zach Burns later today, were partly inspired by this lineage of research into outsourced databases. Now, verifiability isn't something that we're just doing as a virtue signal. It's not just something we're doing to check the box of being a protocol in Web3. We think this is going to have a meaningful impact on the use cases that we see the subgraphs and the graph applied towards. So today, most use cases are front-end use cases, right? Whether it's a read-only app, an interactive app, some kind of DeFi front-end. But there's a host of on-chain use cases that the graph has not really yet been applied to in earnest. You could imagine a subgraph acting as a reputation oracle, as we heard from Yaniv earlier today. You could imagine it being used as a price oracle or some kind of DeFi aggregations. You could even imagine it implementing Yearn-style, automated trading strategies where the output of the strategy is bridged back onto the layer 1 or the lower level chain. And if you really trust the verifiability properties of the graph, you could even imagine using this in a cross-chain state bridging use case. So today we tend to bridge really simple state across chains like a token balance, but imagine being able to bridge any arbitrary map reduce over some other chain onto another chain. These are the types of use cases that become available to us once we take an earnest effort and focus on verifiability. Now, some people in our community have been a little ahead of the curve on testing the boundaries of what's possible. This is an experiment that Dennison, one of the subgraph developers in our ecosystem, ran last year, where he re-implemented an ERC20 token inside of a subgraph, using the subgraph as a read-oriented rollup, where basically just the call data was stored on chain, and then the state of the token contract was basically all written in assembly script. Now, this isn't something I'd recommend doing today with the security model of the graph, but this is the kind of thing that would become trivial to do once verifiable indexing and verifiable queries has been delivered. So to just recap really quickly, write-oriented read-ups, read-oriented read-ups, many of the same considerations. They have a one of n trust model. They have to design bridges. They take advantage of the great unbundling. But the key difference is that write-oriented read-ups are transaction-oriented state machines, whereas read-oriented rollups are arbitrary map-reduce operations, and they're natively provisioned and upgradable. Now, admittedly, over the last few years, viewing the graph as a blockchain has not been our core focus, although I do want to give a shout out to Jackson Blazensky, who's really kept the torch burning on the verifiable queries research, at times by himself, and was integral to founding the cryptography working group within the graph ecosystem. Where most of our effort has been over the last few years, and rightfully so, has been viewing the graph as a decentralized infrastructure market. And the reason we started there is because the graph has had to handle incredible scale from essentially day one. And we're going to get into some of the challenges there, but before we do, because the challenges are daunting at times, let's focus on the benefits and why we're trying to overcome challenges involved in building this in a decentralized way. So all of us are familiar with Web3. I think we've heard a lot of the familiar benefits, like being able to build permanent applications. The graph in particular, I think, is a great example of open source infrastructure. So a lot of us are used to open source software where one developer solves a problem for themselves, publishes as a library, other developers can build on that, remix it. Open source infrastructure gives you all the same benefits, but for actual running software. So when someone solves a problem for themselves by building a subgraph, they've now solved that problem for everyone else that needs to use that type of data. And with the advent of subgraph composition, people will be able to keep building on and remixing with the logic that's already been published to the graph today. So over time, the network will just become this rich tapestry of open, decentralized APIs that you can interact with. Importantly, the service providers that are serving these APIs are completely open and adaptable. That means, there's no centralized entity controlling them. They're responding in real time to incentives, and those incentives lead them to do things like auto-scale, provision more resources, service different geographies, add more database indices, caching layers to optimize their setup. All of that sort of happens in an uncoordinated, decentralized way to deliver a superior quality of service to the end user. And the last benefit I want to focus on today, because it's one that I think we've had some interesting progress on over the last year or two, is just the fact that the graph is Web3 native. And I want to highlight a couple examples of what that means. We heard from a couple speakers earlier today about Constitution DAO running on Juicebox, which deployed to the decentralized network. I think it's super cool that you can actually go to the snapshot vote for the Juicebox DAO, and you can see this DAO provisioning resources to power the subgraph that they used to drive the fundraising platform that then went on to power the Constitution DAO. And a lot of us that have participated in DAOs, we may lament that most of the services that we want to use are outside of the trust boundary of the DAO. So like you might create the advocates DAO, for example, but then that advocates DAO needs a Twitter account, and that Twitter account needs to be owned by an individual. It can't be owned by the entire DAO. The integration points are there. It's not Web3 native. But when you're using the graph, the DAO can natively manage and control their subgraphs using the permission model and structure that's been embedded into the DAO. Another great example of Web3 native capabilities in the graph is the fact that subgraphs are just NFTs. So owning the subgraph confers a number of really important rights to the subgraph owner. You can do things like upgrade the subgraph. You can, migrate the curated stake on that subgraph. And we've heard from a lot of users that, hey, like it's sometimes you want to have, an individual start building the subgraph, then transfer it to a DAO. Sometimes you might be working with a dev shop. And so we solved that problem by just making subgraphs NFTs. And so now they're digitally native, transferable, ownable items. They can integrate with DeFi. You could, use it in all sorts of, DeFi composability use cases. So I think it's a fantastic use case for NFTs that are more than just a JPEG. So what does it take to make a decentralized infrastructure market successful? I would argue that there's three main pillars that are closely interrelated in subtle ways that we'll get into. And those are quality of service, cost of service, and developer experience. So let's get into it. One of the challenges with quality of service, as I noted before, is the incredible volumes that we've been processing from day one. But most recently, it's not uncommon to be over 1 billion queries per day. So that's really why we had to start from the scalability perspective and move towards verifiability. And the other big challenge with quality of service is that it's emergent. We don't control the nodes. We don't control the infrastructure, right? We get to control the incentives, the tools, and the products that we give people to respond to those incentives. We can't directly observe from the blockchain what the uptime of a given indexer is. And despite all those challenges, quality of service is pretty good. Like you can see here that on many days, the decentralized network keeps up just fine with Edge and Node's hosted service. There's even times when the Edge and Node hosted service has had significant outages and the decentralized network has been more robust. But pretty good's not good enough, right? We're operating in a space where people are comparing the graph to Web 2 analogs, where they're used to 5 nines of SLA, right? 5 nines of uptime. So this is something that we want to keep pushing ourselves on until the graph can be as performant and as stable as is humanly possible. A big part of the driver of quality service is the query market. So we have this automated negotiation protocol that you heard a little bit about earlier today, where there's alternating offers between the consumer and the indexer can communicate prices to the consumer using a domain-specific language called Agora, designed by Edge and Node's own Zach Burns. And importantly, when I talk about negotiation, I'm not talking about two humans, sitting at a table negotiating with each other. Hey, how much is this query going to cost that's worth fractions of, a fraction of a penny? That would introduce so much mental transaction overhead that it would completely obviate all the benefits that we get from a decentralized infrastructure layer. Instead, what we're talking about are automated negotiating agents on either side of that marketplace that are in real time optimizing their decisions based on preferences that have been input to them by their respective owners. On the consumer side, we have the indexer selection algorithm. On the indexer side, we have the indexer service that sets prices, and we also have the indexer agent that decides which subgraphs to even index in the first place. And I'm excited to announce that this week, we're launching 2 brand new tools for indexers, one called Automated Agora, and the other that's an allocation optimization tool. And those will be available in beta to try out at GraphHack this weekend. The other benefit to having these agents beyond just making the lives of our users better is that now we can actually run these agents in simulations called agent-based models. So this is a technique from computational social science where we can basically take all these bots, put them in different scenarios, and see what are the emergent properties that come out of that related to cost of service or quality of service? We can do that by both tweaking the behaviors of the agents, but we can also tweak the rules of the protocol and see how the existing agents lead to a different outcome for quality of service. And we have a number of improvements that are sort of on the backlog that we think are going to continue pushing the boundaries on quality of service and cost of service that we're going to validate in this way. Now, when it comes to using agents as a consumer, maybe the indexers can handle it, but most consumers, this is kind of a new pattern, right? We're not used to having robots make decisions on our behalf. In fact, quite the opposite. We're used to technology giving us information that we can then use to make decisions. But here we're flipping the script. Here we need a way of representing what users want so that agents can make automated decisions on their behalf. One way we did this with respect to performance was we looked at cognitive research to figure out where the points of diminishing returns were for responsiveness. So you can imagine that, let's say 50 milliseconds, a DApp loading feels equally instant, and maybe above 5 or 10 seconds, it feels equally terrible. And so we shaped utility curves based on these sort of notions of the value of performance. And then the trick is, how do we give the power to users to actually express how much things like performance, cost of service, data freshness, how much these things mean to them. So this is a screenshot from the Subgraph Studio where the Subgraph developer can modify an API key to decide which of these things they want to value. And then into that experience, we're building reporting tools and predictive analytics to help them understand what is the experience that they're going to get when using the decentralized network that's going to give them the quality of service that they expect. Another big driver of performance is just the number of indexers on a subgraph. As you might imagine, more indexers on a subgraph means there's more likely to be a high-quality indexer with good uptime, the data freshness you need, in the geography that you want. And so another big portion of our focus has been on how do we drive the number of indexers on a subgraph up. Interestingly, a grant from the Graph Foundation to the economic auditing firm Prism Group included equilibrium analysis that related the number of indexers on a subgraph to indexing rewards, basically the square root of indexing rewards over the fixed costs of servicing that subgraph. And so there's this inverse relationship between the fixed costs that indexers have to pay to service a subgraph and the number of indexers we'd expect to service a given subgraph. And that brings me to the next section, the next pillar of success, which is cost of service. Cost of service in the graph today has two main components. One is indexing performance, which I'm not going to spend a ton of time on in this talk because there's going to be a great talk by Sebastian later today, as we mentioned, that I highly encourage you to stick around for. The other big driver of cost is on-chain gas costs. To give you a recap of where we're at today in the network, to upgrade a subgraph, these are April averages, costs about $100. So if you're a subgraph developer, let's say upgrading your subgraph a couple times a month, that's close to $200. And then the costs, the gas cost that an indexer has to pay to service that subgraph for about a month is upwards of $100. And as we just talked about, more subgraphs, more indexers on a subgraph is better than less indexers. So if we say 4 is the magic number, well, now we're up to $420 a month. And so if you're keeping count, we're at $600 total for a subgraph upgrading twice a month. And that's all just gas, right? That's not value that's going to the bottom line of indexers. That's not value that's going into quality of service or DevOps infrastructure. That's just gas. And so it should come as no surprise that the answer here is layer 2 scaling. And today, I'm excited to announce that the graph is planning on migrating its smart contracts to Arbitrum 1. We feel that at this stage in the game, Arbitrum 1 has proven itself. It's been battle tested. It has several $billion in total value locked. It has prominent projects that have migrated to it, including projects like LivePeer that have very similar requirements and economic considerations as the graph. To give you a sense of the impact that this is going to have on the network, in our initial experiments with Arbitrum, we saw about a 26x improvement in gas costs. With the planned Nitro upgrade that Arbitrum has, that's going to both start adding support for WASM, but also introduces smarter compression techniques, we predict that those gas savings will bump up to 73x. And if EIP 4488 passes, which proposes cheapening the cost of call data on Ethereum, we could see those improvements go upwards of 300x. Now, what this means for end users is that upgrading the subgraph could go from $90 on chain today to $125. And the cost of 4 indexers servicing a subgraph for a month would go from $420 to about $5. And what that means is using the graph as decentralized network is going to suddenly become a viable strategy for a huge long tail of independent subgraphs that were maybe too small or priced out of the network as it exists today. The other effect that this is going to have, tying back to the quality of service pillar earlier, is that if you recall, we had the cost of service servicing the subgraph in the denominator. Well, now we expect an upward shift in the number of indexers per subgraph, and we expect this to continue driving quality of service even beyond where we're at today. This is going to be split into several phases. The first phase of this is what we're calling an L2 DevNet. This is going to include an official graph to Arbitrum bridge, wrapping the native Arbitrum bridge. Initially, it's going to have indexing rewards disabled, and the intent is for this to be a place to put like experimental subgraphs and altruistic indexer allocations. And the main purpose here is for us to get comfortable with the Arbitrum model and also give the various downstream components a place to start integrating. And I highly encourage you to check out forum.com, as well as the GIPs that are hosted on Radical. This is the first of several GIPs that are going to be published to explain what that layer 2 rollout looks like. The next phase is monitoring and validation. It feels like every week we wake up to another multi-hundred of millions of dollars bridge hack. And we take the security of the protocol extremely seriously, as well as the fact that the graph is mission-critical infrastructure for dApps that are running in production. So in this next phase, we'll be rolling out new capabilities for the pause guardians in the protocol. We'll be setting up new monitoring infrastructure to make sure that the state of the bridge, as well as the state of token balances on L2 are consistent. And we're going to be rehearsing recovery strategies as an ecosystem, building a better understanding of what it feels like to fail over back to layer 1 or to a fresh layer 2 in the case of a catastrophic L2 failure. And this is also an opportunity for us to iterate on key protocol mechanisms that will benefit user experience, which we'll get to in a little bit. The next phase is migrating subgraphs from layer 1 to layer 2, or as may be the case, migrating subgraphs directly from EdgeNode's hosted service to layer 2. Importantly, state migration will be incremental, and it will be initiated by key users. So subgraph developers will be able to migrate over their own subgraphs, as well as the curation that's been received on those subgraphs. And indexers will be able to migrate their own stake, as well as the stake that's been delegated to them. And at this point in time in the core developer ecosystem, there's no intention whatsoever of moving the graph token anywhere other than where it exists today on layer 1. And phase 4, we hope, is that over time, L1 just becomes a ghost town. It'll continue to be there if we need it, but we fully expect that as the assumptions around layer 2 and people get comfortable with it from a user perspective, that all graph usage will just move to Arbitrum layer 2. To give you a quick idea of the estimated timeline, noting that it's always hard to make estimates in a decentralized open source environment, we expect L2 DevNet to launch by the end of Q3. In Q4, we expect to complete monitoring and validation. and we expect to begin migration of subgraphs from layer 1 to layer 2 by the end of the year. So let's talk about user experience. And when I say user experience, what I really mean is developer experience. And for us, developer experience really starts with the Subgraph Studio, where we do things like give you Subgraph developers tools for API key management, the preferences that I showed you earlier. We have the Subgraph Studio sandbox, where you can deploy and interact with the subgraph locally, all without first having to acquire GRT or interact with the blockchain. But there's limits to what we can do just on the front end with developer experience. At a certain point, we're constrained by the economics. And let me give you a few examples of that. One is the way that bonding curves are used to deploy subgraphs in the protocol today. You heard a little bit about the curation market. It's not as widely known that our curation market uses a 2-layer nested bonding curve construction. When users want to deploy or upgrade subgraphs, they're interacting with one or more bonding curves. And we've seen a lot of the issues you might expect with things like price slippage and also MEV. Prominent MEV researchers today basically say that some level of MEV, which is either minor or maximal extracted value, depending on who you ask, is inevitable. And it's really up to us as protocol and application designers to figure out ways to mitigate MEV at the protocol layer. So on this front, we actually have an exciting announcement. Well, exciting if you're a wonkish protocol economics type, that we call principal protected bonding curves. And without getting too much into the weeds, these are MEV-proof bonding curves that preserve some of the earlier is better dynamics of traditional bonding curves, but where the user doesn't incur any principal risk by interacting with the bonding curves. I highly recommend you check out the GIP in the forums if you're interested in learning more. This was a proposal put forward by Juan DeFago from actually one of our new core development teams that was announced today, GraphOps. One of the other pieces of feedback we hear from subgraph developers is that it's, sometimes they have a preference for modularity for performance and upgradability purposes. And when you do that in the decentralized network, that means now you've gone from interacting with 2 bonding curves to 10 bonding curves, all as a part of your normal development cycle. So part of what will be enabled by things like principal protection as well as L2 gas savings is more complex mechanisms such as signal splitting, which would allow a subgraph developer to interact with one top-level bonding curve to manage multiple lower-level subgraphs, as well as N-1 signaling, where a subgraph developer could leave some signal on the previous version and the next version to avoid any discontinuities in availability for that subgraph. Another really cool mechanism that gets unlocked by both principal protection and L2 gas savings is something that we call signal renting. So one piece of feedback that we've gotten from users today is that having to outlay a bunch of capital by signaling GRT, sometimes in the order of thousands of tokens of GRT, is kind of a unfamiliar and friction user experience compared to what they might be used to using like a SaaS product. With principal protection, it's now safe to let subgraph developers rent signal for some amount of time. And with the lower L2 gas costs, it's now cost efficient for them to top off their subscriptions on a regular basis, whether it's monthly, quarterly, annually, the same way you would expect when using a traditional SaaS or Web2 cloud infrastructure provider. And just to give you an example of just the impact that we expect this to have, there's a quote from Brandon from Pull Together, the CTO there, where he's talking about his interactions with the curation market and just saying how what he really wants is just the ability to pay GRT to have a subgraph indexed. And with all these changes that I've described, both signal renting as well as L2 scaling, we'll now have the capacity to have a single on-chain billing router on layer 2, where a subgraph developer, for all the subgraphs that they're using, can just pay a single subscription that's then intelligently routed to all the downstream places in the protocol where a subgraph developer would typically have to interact today, whether that's curating directly, signal renting, or managing state channel balances, which for us today live on Polygon. So we think this is going to be a really incredible experience that brings subgraphs to parity with what's the state of the art in Web 2 today. So let's put this all together. In the future, based on the research and R&D we've talked about today, the graph is going to be harder, better, faster, stronger. And by that, of course, I mean we're going to have harder trust guarantees as the graph becomes more and more like a blockchain protocol. We're going to have better developer experience powered by new economics enabled by layer 2s, which is then going to drive better query processing performance and better uptime guarantees and all-around quality of service. And I predict that by end of this year, maybe early next year, the graph will have the best quality of service and cost of service of any Web 2 or Web 3 infrastructure layer without sacrificing any of the benefits of decentralization. And finally, I just want to acknowledge that it's impossible to do justice to all the great work that's happening in this ecosystem in a 50-minute talk. So if you're interested in diving deeper on any of these topics, we've already heard about the 5 different working groups today. I highly recommend you checking out the roadmap that was published a few months ago. Hop on the forums, dive into these different GIPs. There's really so much incredible work happening here, and we've really just scratched the surface. And I want to give a shout out to all the new core developers that have joined our ecosystem since the last Graph Day. We really wouldn't be here without them, and I know that the future of the graph is bright because we have all of them on board. And if you're interested in rolling up your sleeves and getting to work and becoming a part of this journey, we've got a ton of open roles to fill, so please get in touch. Come find one of us during Graph Hack or at the party. Thank you guys very much.